Okay, so that's the situation on the classical side. We have these two notions of derandomization, and they're basically known optimally. Yeah.
And just to clarify, like the T-wise independent permutation, the efficiency is like exponential in T or something like that. So up to, is that roughly the dependence on T?
For now, let's just imagine T as being a constant.
Yeah.
So then it doesn't matter.
Yeah.
You also, this efficient here, I mostly put to sort of highlight why we care about them. Later on, we'll have T designs for like exponential T in some sense, and then they're not going to be efficient in N.
Sure.
So this efficient take as a sort of slightly loose, follow.
If you allow expander constructions on the left, I guess you allow your distribution to be close to uniform.
Yes, there are like sort of approximate T designs, but in a very strong notion of approximation. So basically, we'll get back to this, but basically what he does is he has an expander walk on the symmetric group, and you just do a number of steps, and then you're very close to uniform. Very beautiful. Okay, so that's the situation on the classical side. And this QSoft, so we want to do this quantumly. And the quantum version now is derandomizing random unitaries. Also, this mostly will come back to later. Okay, so the sort of most basic questions you have to ask, firstly, how do we even define random unitaries? It's a little less clear because we can't draw such a sort of nice discrete picture. Secondly, do we actually need them? Just because it's a sort of quantum analog of something that's useful classically doesn't mean that we should study it, but we should at least check. Then what are reasonable notions of derandomization? And then finally, what most of this talk will be about is how can we actually achieve them? Okay, I'll take that as a good sign. So I'll begin by sort of giving you the basic definitions of what is called the Haar measure, and which is how we formalize uniformly random unitaries, T designs, which are the sort of quantum analog or unitary analog of T-wise independence, and pseudorandom unitaries, which are like pseudorandom permutations. And then I'll introduce this object that we call the PFC ensemble, which is basically an extremely good T design. And then we'll de-randomize this PFC ensemble using classical results. So these two steps here are from this first paper from the starting slide, and then we'll move on to complexity growth and quantum circuits, and I'll explain how this is related to T designs. And then I'll give a sort of more speculative outlook on how this might be related to something called unitary complexity, mostly because I am here for 2 more days, and I know that at least some of you are working on this T design stuff, so this is more of an ad to like talk to me about this. Also, let me give you the sort of main results so you know what to look out for. So we give the first construction of pseudorandom unitaries with what is called non-adaptive security. We give the first construction of T designs with circuit depth linear and T, which is optimal. We prove what is called a T-independent spectral gap for random classical and quantum circuits. I'll explain what this is. And finally, and I'm not sure, is there any way you can like hide the R? There's a 0.4 here, which I can also try to.
Anyone?
Try this. Okay. And there's a bit of PowerPoint hidden, but that's fine. Okay. And finally, then I'll talk about complexity growth in random quantum circuits. This is known in quantum as the Brown-Susskind conjecture because it came out of like black hole physics. I'm not actually going to say anything about black holes. Okay, so that's the plan. Let's begin by defining what uniformly random unitaries look like. So we'll start from the classical picture and just replace things. So as we all know, quantum state on n qubits is now a vector on a 2 to the n-dimensional Hilbert space. And a state transformation is a unitary matrix on that Hilbert space. And again, we want to study uniformly random state transformations or unitaries. And before I explain how to formalize this, let me just convince you, okay, A, they're obviously, again, fundamental as a uniformly random state transformation, but they're also useful. So in algorithm design, for example, these classical shadow algorithms use uniform, not uniform, but sort of random unitaries in various ways. you want to benchmark a quantum device, you use random unitaries of various forms. In quantum crypto, we can use them as quantum ciphers, essentially. In quantum gravity, they're used to model what's going on sort of inside of a black hole, and so on. So they're actually worth studying. That's my main point. You look like you're about to ask a question. No? Yes. Oh, no, right. Okay, it's a little bit less obvious how to formalize them, right? Because the unitaries is a sort of continuous thing, and you know, it has some complicated geometry, but there's a fairly simple definition, which is called the Haar measure, and this is, in some sense, the correct way to talk about uniformity. The details here are not that important. I put it up because it's kind of worth knowing. In general, the basic idea is you say, okay, if I sample a unitary uniformly at random, so from the Haar measure, and then I left or right multiplied by any other unitary, the distribution should remain invariant, right? So it's a sort of rotationally invariant measure on unitaries. But if you don't want to remember this, and just think of whenever I say Haar measure, it's a sort of reasonable uniform measure on unitaries. Okay, now we're faced with a very similar predicament as for random permutations, which is that these Haar random unitaries, they're useful, they have very nice mathematical properties, but again, they're inefficient to implement. And now, because we're talking about a continuous set, we sort of allow some implementation error. And even if you allow small constant implementation error, again, you can count, and there are too many unitaries at a number of circuits. So you have the same inefficiency problem as for permutations. So again, we want to study derandomizations, and this is now sort of incomplete analogy to the classical case, except slightly harder to visualize because it's this continuous quantum thing. So the analog to T-wise independent permutations is called T-designs. These are families of efficient unitaries that information theoretically reproduce the first T moments of the Haar measure. So this T moments language, you can sort of imagine for simplicity, it's like T queries to the unitary. And if you want a picture, basically what this says is, if I give you some box, and in that box, I put either a unitary that I sampled from the Haar measure, or I take a unitary that I sampled from my T-wise and from my T-design, I'll give you T copies of that unitary in a box. And what you get to do is you get to do some adversarial unitary, apply all of these boxes in parallel to some other unitary, and then you're meant to find out whether the box contains the T-design or the uniform random unitary. The T-design says you can't do this information theoretically, no matter how complicated these unitaries are. That's the picture I have in mind. Okay, the analog to pseudorandom permutations are called pseudorandom unitaries. This is exactly what you would imagine. It's families of efficient unitaries that are computationally indistinguishable from Haar random, adversaries that make polynomial number of queries. This is a very similar picture with two differences. The number of copies of this box that I give you is now any polynomial that you want, but on the downside, the adversary is restricted to efficient unitaries.
Let's say these unitaries are these permutations from before. You have these T-design permutations. If you put them, because a permutation is always a unitary, right? So I could just plug them in here. Does it still hold for a T-design? Like, can I figure out if this is a random? Like, let's say I have less than T of them, can I find out that it's not a random permutation? If I do kind of a quantum test instead of doing like T classical queries.
Oh, you mean as in like, can you find out whether it's a permutation or a unitary?
No, can you
Like
find out, is it a T-design permutation or a random permutation?
Oh yeah, I mean, this is basic, like you can draw the same kind of picture for T-wise independent permutations. There's a question of how do you basically count queries, right?
I think his point was, can you use quantum adversaries to potentially distinguish
Right.
classical design?
That's what I mean by it's a question of how do you count queries. You can make a superposition query over like the T-wise independence is defined with respect to sort of bit strings, right? So I think the question is basically if I do like a superposition query over 5 bit strings, does that count as one query or 5 code or whatever? There's an answer to this, which is you lose a factor of 2. Slightly non-obvious, but we'll actually get back to this later because we'll use the T-wise independence in the construction of the T-designs, and then this will become relevant.
Okay.
Circuits that use the T copies of U sort of with other unitaries in between.
Exactly. So I am prepared
So-
with this. But, technically, this is what is called additive error T designs. And there's a stronger notion called relative error, which is it's even stronger than this sort of adaptive thing. And for pseudorandom unitaries, this is what we call non-adaptive security, because you can't adaptively query the unitary, but you do it all in parallel. And again, there's a stronger security notion, which is called adaptive security, which I'll get back to later again. But for now, I want to take these sort of additive error or non-adaptive definitions as the ones. But yeah, you're right that in general, it's more like there's no, okay, for T designs, you can sort of amplify your way from additive to relative error at the expense of additional depth. And for pseudorandom unitaries, the two are really somewhat different.
Sorry, but in this picture, should you also have some untildes that might be entangled? That you like maybe apply this U tensor n onto half of it?
Yes, you could also have it. So. Any other questions? All right, so what we'll do in this talk is we'll sort of give a unified construction of both of these objects, basically by first coming up with a sort of very good T design, and then we'll plug in T-wise independent permutations and get T designs, or we'll plug in pseudorandom permutations and get pseudorandom unitaries. That's the plan. Okay, now before I go there, let me give you a brief rundown of at least some prior results. T designs are like a very old field, so there's a lot of literature here. This is not an attempt to be exhaustive, but it's mostly to give you kind of sense of what people are going for in this field, which is basically low depth. This is the main thing that we care about. And what I mean by low depth is, if you have a T design, what's the depth of the unitaries, the quantum circuit depth of the unitaries in that ensemble? And in this famous and very nice paper from 2016, Brandau, Haar, and Horodecki proved that if you just take a random quantum circuit, some reasonable model of what a random circuit is, these will form T designs in depth n squared times t to the 10, where n is the number of qubits and t is the t from the T design. Okay, so this is, it's a polynomial. It's not an amazing polynomial, especially the t to the 10 is not great, but it's a polynomial. But what you would really like is to get these exponents down, and in particular, you want to get the t to linear. Optimal. If you do it for random circuits, later, this has sort of fairly fundamental consequences for their properties. So 2 years ago, Jonas Haferkamp proved that actually he can, it's a sort of refined analysis of the Brandau et al. Paper, and he gets n times t to the pi plus little o of 1. And earlier this year, Haar, Liu, and Tan showed that if you use sort of cleverly engineered circuits rather than random circuits, you can actually get it down to sort of O tilde of n times t squared. And all of this holds up to exponential moments t. And there's another paper which is concurrent with this HLT paper, which is sort of slightly worse. And finally, there's a paper from 2017 that actually does get the optimal, like linear and t scaling, but only for extremely low moments. So really, there are two parameters to care about here. One is the depth, like how does, especially the t dependence is what we care about. And this we want to be linear, but we want to have it for ideally any moment, but realistically for up to exponential moments. Okay, so that's the big open question here is, are there T designs with that linear and T even for high moments? Okay, this PRU story is slightly shorter, and this is basically a quest for like general adversaries. So this notion of PRUs was only defined in 2018, actually, by Ji, Liu, and Song. And they defined it, but what they could prove is pseudorandom states, which are basically pseudorandom unitaries where your adversary only queries on the all-zero pattern. Okay, so it basically only sees like the first column of your unitary, and this is all that it has to tell the two distributions apart. So this is obviously extremely restricted, and then basically it's been a game of, can you make this adversary more and more general? And last year, Liu et al. Gave a construction of what they call pseudorandom state scramblers, which are PRUs where you can query any IID tensor product state, but you can't have entanglement between the sort of queries that you make. And there's another paper that by Anand et al. That gives pseudorandom isometries, so sort of from a small space to a big space, again, for IID tensor products or IID Haar random states. So these are all extremely restrictive adversaries that you allow in your distinguishing task. Okay, so the question here is very simply, do PRUs, in the sense of against general adversaries, exist? Okay, so these are the two open questions that we want to answer, and we give affirmative answers to both. So we prove that you can construct T-designs in depth n log n T, even up to exponentially higher moment. So we get like T less than or equal to 2 to the n over like 2.0001, like any constant bigger than 2. And this is for exponentially small additive error. On the PRU side, we prove that we have a construction of PRUs that we can prove is secure against non-adaptive adversaries, assuming quantum secure one-way functions. And because Ron already asked about this, what about adaptive adversaries? We can prove that if you allow isometries where you add, like, say, log squared n extra qubits, then actually our construction, or like a slight modification of that, is even secure in this most general adaptive model. And finally, I'll mention that Ma and Huang, this is unpublished, but they've given a proof that our construction is actually secure against adaptive adversaries too. So this is a sort of slightly more careful version of the isometry proof that we have. Okay, so these are the main results from this first paper. And now let me tell you how we achieved them, which is via what we call the PFC ensemble. So sort of high-level idea here is the following. We understand classical derandomization like really well. We have basically optimal constructions for everything. So if we could imitate the Haar measure like really, really well, using only classical randomness, maybe huge amounts of classical randomness, for now we don't care, but using only classical randomness, then we can go back to the classical literature and de-randomize that classical randomness to get T-designs and PRUs. That's basically the plan, right? So slightly more precisely, and what we mean by imitate is we'll construct T-designs for exponentially large T using uniformly random functions and permutations. And then we'll replace these uniformly random functions and permutations using their T-wise independent or pseudorandom counterparts classically, and this will get us T-designs and PRUs. Okay, so that's the plan. It's a sort of two-step thing, right? And the second step of replacing them is really quite easy. The main difficulty is how do we find, how can we basically reduce this quantum Haar random notion to just classical randomness? Okay, so that's the plan. Here's how you do it. You multiply three things together. This is what's called the PFC ensemble. So we take a uniformly random basis state permutation, that's the P. And just to be clear here, by basis state permutation, I mean like a permutation of the basis cats, right? Not a permutation of the qubits in that string. So if you write it out on 3 qubits, it's some sort of permutation matrix. You multiply this with a uniformly random binary phase, so some diagonal matrix with uniform signs. And then you multiply that with a uniformly random Clifford unitary, so a unitary that is only made up of Clifford pairs. Okay, so firstly, this does only use classical randomness, essentially, right? The basis pair permutation and the binary phase are classical randomness. The only sort of quantum randomness here that's left is a uniformly random Clifford. But the Clifford group is really tiny, so this is actually like a very small amount of randomness, so we're not really gonna care. Okay, so that's yes.
Where's the dependence on T in this construction?
There's no dependence on T, like the construction is independent of T.
So this will work for arbitrarily high moments?
Well, okay, let me, like a good segue. So what we prove is that this is a T design with additive error that's T over 2 to the n over 2. N is, the number of qubits on which this acts. This works for all T, but once T becomes bigger than 2 to the n over 2, it's a trivial statement, right? So really, this is where I said earlier, we get it up to T, like 2 to the n over 2.0001. This is where this comes from, right? Because as long as T is an exponential that's smaller than 2 to the n over 2, this is exponentially decaying error.
Can you remind me of something classical? Are the unitaries generated by reflections?
What do you mean?
So if you would just generate random reflections and compose them together, would you get a random unitary?
Ooh, like random.
Maybe I'm thinking of real space instead of complex space.
Yeah, yeah, there is a method to generate random, like uniformly random units with dimension based on this reflection. Yeah, I have a small, like a note on this.
And are the unitaries also generated then by this PFC construction? Is any unitary representable by such a PFC?
Now this is an excellent question, and that's basically the speculation part that I'll go to at the end. The answer for now is no. There's a difference between, so there's a notion called epsilon nets on unitaries, which is basically this. It's find a unitary that's close to any unitary, like for any unitary, find one that's close. This is not an epsilon net. It just says that if you restrict the number of queries essentially that you make to your unitary to be 2 to the n over 3, let's say, then you can't tell apart which distribution you sample from. But it's not like a for every unitary there exists a PFC kind of thing. Also, just as a reminder on what this key design thing means mathematically, it means you can make any state now, and there are no restrictions on this state anymore in contrast to the previous works. And then you sample either a Haar random or a PFC unitary, and on average, if you apply the unitary t times in parallel, these two states are close in place distance.
But I mean, I guess it is an epsilon net for some fixed epsilon. I mean, it's like this is a finite set. And for a given thing.
Yeah, I mean, it's for a very bad epsilon.
Is there a diamond norm statement also?
Yeah, so these states here could have ancillas. And so the sort of more formal version is you look at the respective twirling channels, the diamond distances. Any other questions?
I mean, just out of curiosity, it's so simple. So is it easy to do anything better if you just do it twice or something? I just add another C, a P, and an F, and then I get better than 2 to the n over 2. Or do you know that this is kind of the best you can do?
We don't know that it's the best we can do. We hope not. But there's no obvious modification that you can make. I mean, you can, by repeating, you can get down the error, but you get like sort of exponents, but you don't, like the thing that we would care about is if the span works for even higher t, right? That's the range that you want to expand. And there's no sort of obvious way of doing that I know of, but if anyone knows one, you know.
I find it surprising that these plus minus 1 pairs are sufficient. That's really like each other. It's like basically the complex numbers, they come from only the proof.
I mean, so as you might have noticed, I didn't give like any intuition or proof sketch for this, which is not, it's kind of because there's very little intuition for why this works outside of the proof. So within the proof, there's sort of, I mean, we played around with this for a long time, right? And until you find this sort of specific thing, and within the proof, there's a lot of intuition for what the things do. But outside of the proof, there's frankly very little. I can give you, this is a technical aside, I can give you a very short version of why the binary phases are not worse than general phases, which is that the random Clifford basically allows you to reduce to a subspace where you don't have collisions between computational basis states between the copies. And if you have that property, then a binary phase versus a uniform phase, if you take the expectation, they don't actually behave differently. So you don't get sort of cancellations from the binary phase that you wouldn't get from the uniform phase. And this is kind of why the binary phase is enough. But yeah, that's a very limited amount of intuition.
Is there some easy way to adapt this to orthogonal group, like to replace the reports by something real?
We haven't tried. I personally don't know why orthogonal designs are as relevant. So that's why I haven't tried, but possibly. Okay, so what have we achieved and what have we not achieved? So we haven't solved the problem, right? This is I call this a T design here, but this is not efficient, right? In particular, the uniformly random basis state permutation and binary phase are not efficient. You can't sample from them. They basically use uniform functions, which again, there's too many of them. So these are not efficiently implementable, but they basically only use classical randomness. Again, the random Clifford we can kind of ignore because there's so few Clifford unitaries. Okay, so this PFC thing basically reduces Haar randomness to classical randomness. This is what it does. Okay, and now the rest of this is relatively easy, right? To get T designs, what you do is you just take the PFC and you replace the random function and permutation by T-wise independent counterparts. And for this, there are optimal constructions that are known. So this is doable in depth and log n T. This is this Kasparov construction that I mentioned earlier. And now the security proof, if you want to call it that, is fairly simple, right? You just look at, you basically go back to the PFC ensemble, right? You have your T design. You're like, well, okay, I only look at the Tth moment, or this is where the spectral of 2 comes in. It's actually the 2 Tth moment. You can write this out explicitly, and then you see that it all goes through. And then you go back to the T design property of the PFC ensemble, and they're done. So that's a very simple replacement. And the total depth that we get is n log nt for the permutations and the phase from this Kasparov construction, and then order n. Okay, so this is how to get linear depth T designs. On the PRU side, it's kind of even simpler because you don't need to worry about any factors of 2 and T-wise independence and so on. You really just take the PFC, you replace the random function and permutation by their pseudo-random counterparts. Now you have to use quantum secure pseudo-random functions and permutations, so those are known. And then you're done by a basic hybrid argument. You just say by security of the pseudo-random functions and permutations, the adversary can't tell whether I used the PRUs that I constructed this way or the PFC. The PFC is indistinguishable from Haar random, so okay, and then for the isometries, basically what you do is you take the PRU construction on like n plus little omega of log n qubits, and you fix the little omega log n qubits to the all plus state. Which is really just a technical trick to make sure that there's kind of very low probability of collisions. Because if you have a plus state on sort of super logarithmic number of qubits and you measure that, and then you take another copy, you measure it again, you have a negligible chance of getting the same string. And that's the property that we need for the adaptive security. So this is why we need these sort of extra input qubits. Again, this has now been sort of replaced by this Mark 1 proof that doesn't actually need these extra qubits. Okay, this is all I want to say on this PFC stuff. So this is basically the results from the first paper at the start. So if you have any more questions on this, now is the time to ask. Yes.
I was just curious, what about inverses? Like if let's say I want a notion where I also give access to U dagger or something.
Yeah.
Do these constructions still work?
So this construction doesn't work for inverses. Basically, because if you take, like if you take the PFC and inverse, you get like a, so you do like PFC dagger, right, which is, okay, these daggers don't matter. So you get permutation, phase, and Clifford. So if you put in a computational basis state into this will be another computational basis state, and this will just add a global phase. So basically, this will still be a computational basis state.
And you can just learn the Clifford basis.
Right, and then you just learn it. So it doesn't work with inverses. But it turns out that if you do the following amazing trick, you add one C, now it does work with inverses. So it's like very close. This is also from Robert and Clemmy's paper. So yeah, you have to add one extra Clifford. It's not a trivial proof that it works for inverses, but it does. Any other questions? Yeah.
Why the focus on depth rather than size?
So the regime that we're interested in ultimately, which is what we'll get to with the random circuits, is basically the regime of like very, very large t compared to n. So n being t being like exponential and n. And then the extra factor of n doesn't really matter.
The sizes of your actual constructions, like, are they kind of reasonable, or do they use a ton of ancillas and a ton of extra gates?
Oh, I mean, these don't use, well, okay, you do technically need ancillas, I think, to implement permutation or something, but it's a very small number. So the size is very reasonable. I mean, okay, we haven't worked out the constants, right? So asymptotically, the size is a very reasonable polynomial n. I presume it's n squared, maybe n squared log n or something. The constants, we don't know.
Like this permutation matrix, is this not just a swap circuit? Like a lot of swaps in there? Or is there a representation where you just add a lot of swaps?
Yeah, you can. Yeah, I don't know what the depth of that would be. Like the problem is you need a, like, so there's always like in the limit of infinite depth that converges to that versus at sort of very concrete finite depths. And those two things. Hey, if not, what the hell am I doing? Then let me move on to the complexity growth of random quantum circuits. So this is from the second paper that I mentioned at the start. So I've been telling you about how amazing this PFC ensemble is. Here are the reasons it's not perfect. Firstly, we only get additive error T design, right? This parallel security version that I had on the slide. Whereas ideally you would want relative error T designs. And also just to be clear, the rest of the talk is now purely about T designs, right? We're done with PRUs. We sort of solved PRUs and we're moving on. So you would want relative error T designs, which would imply security against adaptive adversaries. Secondly, the PFC is a very, very structured circuit, right? It's this Clifford, the phase, the commutation. It's not a random quantum circuit. And ideally, you would want T designs from random quantum circuits. I guess they're like more simple to implement in practice, but at least for me, it just feels like a more fundamental statement because it tells you how a random circuit sort of interpolates between like identity matrix and a Haar random unitary, right? So if you let a random circuit run for like infinitely long time, this will converge to the Haar random distribution. And then the question is, if I cut off the depth of the random circuit at some number, how quickly does it converge to uniform randomness? Right, so if you could prove a T design statement, especially linear in T, for random circuits, that would tell you that random circuits kind of very smoothly, linearly interpolate between like, identity matrix and uniform randomness. And that's more for philosophical reasons like that. Finally, we only get T designs for T less than this exponential here. And you mentioned these epsilon nets. If you could get T designs for even larger T, then you would at some point get epsilon nets. So there's some sort of motivation, at least from a purely mathematical point of view, of studying the behavior even as T goes beyond this limit of exponential. So in the rest of the talk, I'll address the first two questions. The last one is still open. But the first two we can actually resolve. So we'll talk about random circuits, and just so that we all know what a random circuit looks like is a picture. Imagine you have like 6 qubits in this case, and there are various models of random circuit, but the one we'll use is this brickwork model, where you place 2 qubit gates in this kind of brickwork arrangement, and you just sample each 2 qubit gate uniformly, independently from SU4, like the group of 2 qubit unitaries. And this is what we call one layer of the circuit. And now, as I said, the question is basically, as I keep going with this random circuit, you know, how random does it look? How quickly does it converge to the uniform distribution? And this is measured by the t-design property. So what we prove is that if you take a random quantum circuit of depth O tilde n t, and you know now there are no n psillas, so the size is just an extra factor of n. These are t-designs with exponentially small relative error, but okay, now it's t up to n over 2 to the n over 6. Okay, so this resolves the first two bullets from the previous slide. It's now for random quantum circuits, and it's exponentially small relative error, so it's secure against adaptive adversary. Okay, this is basically what this 2016 paper by Brandau et al. Sort of was going for. So it's nice that I guess this is finally resolved. Okay, now I'll have like one technical slide. You can just zone out for one slide if you don't want to hear the technical. Yes.
What does SU stand for?
Oh, it's like the special unitary group on 2 qubits. Just imagine it's like the 2-qubit Haar measure. Okay, so here's the one technical slide, which is basically I want to give you at least a flavor of the proof ingredients that go into this random circuits. Okay, so the viewpoint to take here is that a random quantum circuit is a random walk on the unitary group. And basically, if you look at this, the way to imagine this as a random walk is you start at the identity matrix, and this first layer is like one random step on the unitary group. It gets you from the identity matrix to some other unitary. And then the next one starts from that unitary and does another random step and so on. Right? So in this manner, you can view a random quantum circuit as a random walk on the unitary group. And now really this is a question about how quickly does this random walk converge. So in some sense, it's a sort of question about the geometry of this random walk. It's kind of useful to think of graphs for a second. So suppose you have an expander graph and you do a random walk on that. We all know that sort of the defining property of an expander, if I do an expander, like if I do a random walk on an expander graph, I converge very quickly to the uniform distribution on that graph. Whereas if I have, say, like a line graph that's just like this. Basically, the problem is, suppose I start here, I like go here, I go here, maybe then I go back, and I get here, and so on. I basically have a lot of redundancy in my walk, right? I don't make progress every time. I go back a lot, and I backtrack, and I don't converge nearly as quickly. So sort of from a geometric point of view, if you like, the question here is the random walk of random circuits more like an expander walk on the unitaries, or is it more like this kind of line walk? Now, the way to sort of quantify this is by what is called the spectral gap of the random walk. I'm not going to define this, but the important fact to know is, I mean, if you want an analogy, it's sort of like the eigenvalue difference in expander graphs, right? The important fact to know is the spectral gap has a dependence on t, the moment. And if you can prove that the spectral gap is some constant independent of t, then you get relative error t designs in linear depth. So that's what we want to prove, this t-independent spectral gap. Okay, how do we prove it? Well, firstly, we reduce the random quantum circuits problem to a different problem. And what we prove is that if you take any random walk on the unitaries with a sort of special structure, and the special structure is that each step of the random walk samples uniformly from what we call a local subgroup. This is some subgroup of the unitaries that only acts on the constant number of qubits. So if you have any random walk that has this sort of uniform local subgroup property, we can prove that the spectral gap for this random walk, the t-independent one, implies a spectral gap for the random quantum circuits. Okay, so why is this useful? It tells you that instead of having to prove the t-independent spectral gap for the specific random quantum circuit distribution, you can now go ahead and engineer some walk that has more useful properties in your proof. As long as it has this local subgroup structure, you're fine. All you need to do is prove a gap for that one.
Sorry, maybe I can relay a question here. What exactly is a t-independent spectrum?
Yeah, well, I didn't want to explain this. So there's a moment operator associated with a random walk for each moment t. And you basically look at the spectrum of that moment operator, and you look at the spectral gap of that thing. And the question is, does it decay in t or not? It's not really relevant here, just a sort of buzzword that this whole Markov chain literature uses, so it's useful to have seen, but what you should just think of is basically like the expander constant in a graph, which is also a spectral gap of Euler class.
This local subgroup is the generator of the Cayley graph on this unitary group that you're using to define the graph that you're walking. Okay. So you have this, the steps are elements from this local subgroup. So this local subgroup generates this Cayley graph on the entire unitary group.
I mean, it's not going to be a discrete set, so it's not like a graph, but it's sort of like continues
Okay, graph.
Yeah.
Yeah, I guess I'm also wondering about the T independent. What is the property of this local subgroup you need for the expander? That's this T independent spectrum.
Yeah, the T independent, just think of like it behaves like an expander in some sort of well-defined continuous sense.
Mm-hmm.
I mean, I haven't said anything about how to construct this walk yet, right? I've only said we've reduced the problem to we can now engineer a walk rather than having to deal with a specific random quantum circuits walk. And now you'll probably guess where this is coming from. So we start from the PFC thing, which you can also view as a walk. You can just view one sort of PFC as one big step of a random walk. And we know that this PFC ensemble basically mixes very well as a random walk because it's such a good T design. Our strategy will be to start from the PFC. The problem is the PFC doesn't have this local subgroup structure, but it does have a spectral gap. And we basically want to replace the PFC by like little steps that have this local subgroup structure while preserving the spectral gap. Okay, I know that I haven't defined spectral gap, so every time I say spectral gap, think of sort of expander-ness of the thing. Okay, the first step is a kind of technical, silly step. You replace the PFC by like Clifford permutation, Pauli Z permutation Clifford. The only reason I put this here is so that it's obvious that the only thing we really need are permutations and Cliffords, and the functions have disappeared. Okay, now what we'll do is we'll take this CPZPC thing, and instead of doing one big uniformly random Clifford followed by one uniformly random permutation, we'll take random walks on the symmetric group, which we get from this Kasabov paper, and a random walk on the Clifford group, which you can construct fairly easily because it's a tiny group. And instead of doing the uniformly random step, we just do one step of first the Clifford walk, then we do one step of the spectrally gapped walk on the symmetric group, then we do the Z, then we do another random step of the expander walk on the symmetric group, and then another one step of the Clifford. Okay, so we basically, instead of doing the uniform steps, we do like tiny steps. But we know that each of these tiny steps is itself a gap walk. Okay, now you can prove, because each of these tiny steps now has a lot more local structure. It's basically like doing one gate instead of the full circuit. You can prove that these have this local subgroup structure that we need. And then finally, you can prove that if you stitch all of these spectrally gapped walks together, you get one big spectrally gapped walk. So that's the final walk that we're looking at, is this CPZPC, but with one tiny step instead of the uniformly random Cliffords and permutation.
So is it that you, like in this CPC, that you just pick a random generator of a Clifford group, or like a random transposition or something?
Yeah, the Cliffords are very easy, right? You just, basically anything is spectrally gapped on the Clifford group because it's so small. The difficulty is the permutation.
So can you just take a random transposition if you switch the elements? Maybe.
We just end up taking, I think, one layer of the Clifford circuit, which we can prove is spectrally gapped. Because it's like the simplest to relate to this local subgroup structure. But the Clifford walk is really a bit of like math. It doesn't matter that much. Right, now maybe let me move on from this to circuit incompressibility, and then we can discuss more technical questions afterwards. So, okay, what have we achieved now? We've proven that a linear depth random quantum circuit is a T design. How is it related to circuit complexity? Well, the question that it allows us to answer is a sort of very basic one, which is if I give you a random quantum circuit, this circuit will implement some unitary. I can ask whether there's a different shorter circuit that implements the same unitary. Okay? So in other words, does my random circuit basically sort of have a lot of shortcuts in it that I can skip if I'm clever? Or is the random quantum circuit almost the shortest circuit that implements that particular unitary? And perhaps surprisingly, this wasn't known. It wasn't even known for classical circuits. And the conjecture which came out of high energy physics is that the answer is no, you cannot compress a random quantum circuit even at exponential depths. So the higher the depths, the sort of more room there would be for shortcuts, and the conjecture is even at exponential depths, you cannot compress this. This is known as the Sprank-Susskind conjecture. Okay, and we can finally prove that this is actually true. So what we prove is that with overwhelming probability, even an exponentially deep quantum circuit is incompressible after sort of small polynomial factors in n and constant approximation error. So you cannot even find a constant error approximation to that unitary that has a much shorter circuit depth. Okay, and the proof here is fairly simple by counting. We have already shown that the random quantum circuits of depth order T are T designs. By counting, you can prove that most unitaries in a T design must have circuit complexity at least T over poly n. And the classical result, by the way, also holds. And now you can just put the two together and say, well, okay, if I have a random quantum circuit, I know it's a T design, I know I must have at least this. So this part is fairly easy. Really, this is a simple corollary of the T design statement for random quantum circuits. Okay, just for completeness, we also proved the same for classical circuits, which surprisingly wasn't known. It's been open since '96. So again, you prove a T-independent spectral gap, and this gets you T-wise independent permutations from random reversible circuits. And it also gets you an analogous incompressibility result for random reversible circuits. This is Q sub, so this is okay, before I go there, are there any more questions on the sort of circuits part of the part?
In a classical case, you just draw the corollary from two results which are in principle available, right? So evaluated, right? Is that correct? Or what was the extra ingredient that you provided for this classical process?
So really the extra ingredient is that there's a Spandau walk on the symmetric group due to Kasabov.
Yeah.
But the question is, what's the circuit depth of implementing one of the steps of the experiment?
Yeah.
And A, okay, this hadn't been analyzed, and B, we actually have to modify the one somehow. The depth smaller.
Okay. So
the Kasabov thing is a purely combinatorics result. It's like here, it's in principle constructive, but it's a sort of math idea of the constructive proof, right? Isn't like there exists, pick whatever you like. So you have to actually find a specific instance of this, which is very short.
You didn't think of it, so
That's the difficulty. Yeah.
Do you know anything about the polynomial? Like, I was just curious, like if I have a random circuit of size n to the 100 or something, do you know, like, oh, there's probably no circuit of size n to the 50 that does the same thing?
We could, in principle, know something about the polynomial if we just sat down and did it. So if you want to know, I can probably even sit down for you and do it.
Oh, I don't have an application, I was just
We
curious.
haven't done it. So. Okay, then let me end on some speculations that I hope some of you might be able to have some input on. And this is how this sort of random circuits business is connected to what we call unitary complexity theory. So let me give you the one slide pitch for those of you who've been at QIP, you've seen this. but for those who haven't, let me give you the one slide pitch for unitary complexity theory. The idea is basically that we have all of this zoo of quantum problems here that are basically quantum input, quantum output problems. They're not decision problems. And these we call fully quantum problems, or unitary synthesis problems. And they're really about mapping one quantum state to another. So for example, breaking commitments in quantum cryptography is about mapping one state to another. It's not about solving a decision problem. And you could hope that this just reduces to decision problems, just like search problems usually do. But there's decent evidence that this is not the case. So for example, there's a paper from 2 years ago by Kretschmer et al. That proves that even if p is equal to np, certain quantum crypto primitives can still exist relative to some oracle. And the interpretation of this for our purposes here is that breaking quantum crypto is a unitary synthesis problem. And just because some decision classes collapse doesn't mean anything about the unitary classes collapsing. Okay, so what we started to do sort of in the last year or two is sort of build out basically like an alternative complexity theory of these unitary synthesis problems to define classes and group them, group reductions, and so on. As I'm happy to talk about this more afterwards, but I want to mention here is how are unitary and decision complexity really related? And the sort of crispest version of this question is what is known as the Aronson-Kuiper unitary synthesis question, which is the following: can every unitary be approximated by a circuit of the following form? So this is basically your question from earlier in some form, which is, have some fixed unitary U1, then some Boolean function, say as a phase oracle, another fixed unitary Boolean function, and so on. And the question is now basically, formally, for every unitary, does there exist a choice of Boolean function such that this circuit on, say, the first n qubits, this might have ancillas, implements the unitary approximation? Why is this sort of, why does this talk about the relationship between these two notions of complexity? It basically asks, in some sense, can I reduce the complexity of the unitary purely to the complexity of implementing a classical function?
Sorry, so these U1, U2, these are fixed?
Yeah.
But how long? Like it's just K?
It's K is some polynomial. So you want to have some unitary on n qubits. You allow yourself like polynomial and n depth, polynomial number of queries. Also versions of this where you want the U1, U2 to be efficient, others not. But it doesn't really matter for what I want to say. Okay.
So if you ask for implementing a unitary, why not let U1 be the unitary? That is something strange.
So yeah, the U1 to UK, they're sort of universal. They're the algorithm. And the only thing you're allowed to vary is the function that you put in.
Oh.
So the question is, as I vary the function that I put in, can I in some sense hit every unitary?
The question is, does there exist fixed U1, U2 of
Yes.
UK such as this book?
Yes, so the U1 to UK is fixed, and the only thing you vary is the function. The question, do I hit everything?
Then you immediately get into a counting problem. No, there's like 2 to the 2 to the n functions, but there's probably an exponential higher number of unitaries.
2 to the 2 to the 2n, the unitary. So as long as you have like same number of ancillas as you have qubits that you act on, counting unfortunately doesn't get you anywhere. That's like the first thing you would think, right? So, oh, so many unitaries. But yeah, this is why you definitely need ancillas, which is why I've sort of drawn them. But as soon as you have ancillas in your function, counting doesn't seem to get you anywhere. Okay, so this asks, can I reduce the unitary implementation to implementing a classical function? It doesn't, it doesn't fully say this. It doesn't ask, for example, how do I find the function? Okay, that's a separate question. But in first instances, does the function exist? Not much is known. The only thing is known that you need more than one query, which is maybe not that surprising if you look at it from a sort of Lie theory point of view. What I want to suggest is that this is essentially an epsilon question. Right? It's usually studied by quantum sort of algorithms people, but really it's about, can I find an epsilon net of this form? And this PFC ensemble looks like a promising start, right? Because it in some sense reduced Haar randomness to classical randomness. So in other words, it said, here's like, if I vary the permutation and the P and the F from this large set of classical functions, then I don't hit every unitary, but I sort of imitate the Haar measure very well, which does mean some sort of uniformity on the set of all unitaries. So basically the question that I would like, an answer to, and that I've been thinking about, and that I would invite all of you to think about is, can we somehow modify this PFC ensemble, maybe add more ancillas, maybe add more steps or something, to boost this from just a very good T design to actually an epsilon net? And, with that, then have a positive resolution to this unitary synthesis question.
I think I'm still a little confused on what F does. Like, is it do I have a Boolean circuit that outputs like some phases and that I have?
Yeah, it's a phase oracle. So it's like, yeah, it's the, yeah.
And is it bounded in any way? Like, let's say I wanna. So I have information about my unitary. Can the Boolean circuit be very complicated to find the phases, or?
Yeah, so there is a regime where the answer is yes, which is basically if the function has exponential, like I forget the exact exponential, but it has like a huge input size.
Yeah.
So say the input size of the function should be restricted to polynomial in n. It has to be, as we've established by counting, it has to be at least 2n. But you don't want exponential inputs, because then you basically are just like, you tell the function which unitary you want. I think that you can do it. Yeah, I hope that this PFC thing, because it does reduce our randomness, the classical randomness, maybe gives us a starting point on this. This has been open since 2007 or something, so it's good motivation to try. Yes.
So this PFC, like, if you repeat it, like, what is the orbit of these groups and maps? Does it, you still get it? Like a finite, so it does not become an epsilon net if you.
Not that we can prove. Basically, the problem is as soon as T, so, okay, you can try to prove that it's an epsilon net directly. I don't know how to do that. You can try to prove that it becomes an epsilon net by proving that the T designed for like extremely large T. I think it's like T is 2 to the 2n, like something like that. You probably know better than I do, actually. And the problem is by just repeating, you don't get beyond this T has to be less than 2 to the n over 2 restriction. So it pushes down the error in the T design property, but it doesn't extend the range of T, which is what you. Okay, so with this, let me wrap up. These are the 4 results that I promised at the start, that I hope I've convinced you do indeed exist. On the PRU side, some open questions are, well, the obvious one was adaptive security and inverse security, which has now been solved. The other one is, frankly, applications of PRUs. Not quite sure what happened in quantum crypto, but we all decided we had to construct PRUs, and no one really bothered to check what they were useful for. So now we have constructed them, and we should maybe find uses for them to at least have some post-hoc justification for all that. And there are some applications, but they're all kind of like a little contrived, frankly. So especially in quantum crypto, you would imagine that this gets you like that unclonable encryption, say. We don't know how to prove it. As far as I know, nobody else knows how to prove it. But yeah, this is, now that we have them, this is the time to actually find crypto applications. On the T design side, as I said, the main one for me is this Aronson-Kuperberg conjecture. And finally, we now have finally these asymptotically optimal constructions. So it might be the time for constants. So if anyone is actually willing to work out the constant and try to make them as tight as possible, now that we have the asymptotic constructions, this, I guess, is the time to do it. All right, I'll stop here.